Today we discuss section 20. In this section we discuss two major theorems, Fermat's theorem and Euler's theorem. The first one is called Little Fermat theorem. A is an integer and P is a prime number, not dividing A. Then P divides A raised to P minus 1 minus 1. Okay, that means A raised to P minus 1 is congruent to 1 mod P. So we need to prove this congruence relation, or this A raised to P minus 1 minus 1 is a multiple of P. For that we consider ZP. We know that ZP is a group. Obviously this is an example of a field also, under addition modulo P and multiplication modulo P. So if you consider this field, as this is a field, every non-zero element of ZP has multiplicative inverse as well. Okay, so what is the cardinality of this field? Okay, this field has, since this is a field, then what is the definition of field? ZP under addition modulo P is an abelian group. Abelian group. Also, ZP minus 0, that is non-zero elements of ZP, under multiplication modulo P is also an abelian group, and we have distributive properties. Okay, so this is the definition of a field. As this ZP is a field, we know that every non-zero element of this group has a multiplicative inverse also. Okay, and we know that if we choose any non-zero element, say B belongs to ZP minus 0, then we know that since the cardinality of this group, this non-zero element, the collection of non-zero elements, the cardinality of this group is P minus 1. So if we choose any B belongs to ZP minus 0, then we have, if we operate B P minus 1 times, okay, P minus 1 times, then we will get the identity. Okay, what is the identity? Identity is 1. Okay, so B to the power P raised to the power P minus 1. So this is P minus 1 times, that is 1. Okay, what does it mean? When you multiply B P minus 1 times, okay, then you take the remainder when it is divided by P, that will be 1. Okay, that means if we consider B raised to P minus 1, this is the product of this, then you write this is a multiple of P times Q plus 1, then the remainder is 1. That is the meaning of this statement. Multiplication modulo P means if you multiply all these elements and divide it by P, then the remainder is 1. So what does it mean? B raised to P minus 1 is equal to multiple of P times 1. Okay, so what does it mean? This shows that B raised to P minus 1 minus 1 is a multiple of P. So if we choose any non-zero element, say 1, 2, 3, etc., P minus 1, we know that if you take any element of this set, take B as any element of this set, then we have this result. So we need to, in order to prove this theorem, we need to prove this is also true for every integer which are not multiple of P. Okay, so not only this B from this set, we need to prove the general case. Okay, so if we choose any arbitrary element A belongs to Z, but P does not divides A, that means A is not a multiple of P. Okay, now you can write this A as A is congruent to, or A can be written as a multiple of P times R. Okay, what is the importance of this R? This 0 is less than or less than R less than P minus 1, because we assume that P does not divide A, so A is not a multiple of R, multiple of P, then this R will not be 0. So R is always a number in between P minus 1. So immediately you can write, since this R is a element in between 0 and P minus 1, so R is a member of this set as well. So this R raised to P minus 1 minus 1, or you can write R raised to P minus 1 congruent to 1 mod P. What is the meaning of this? R raised to P minus 1 minus 1 is a multiple. Okay, but we know that if you consider A raised to A is from this you can write A is congruent to R mod P, right? That is A minus R is a multiple of P. Okay, that is the meaning of this statement. A is congruent to R mod P means A raised A minus R is a multiple of P. whenever A is congruent to R mod P, then we know that A square is congruent to R square mod P. Okay, because you can multiply two congruents, A congruent to R mod P, then we multiply these two equations, you will get A square is congruent to R square mod P. Similarly, A raised to 3 is congruent to R raised to 3 mod P. In general, A raised to P minus 1 is congruent to R raised to P minus 1 mod P. Okay, so what does it mean? This means that A raised to P minus 1 is congruent to R raised to P minus 1 mod P. Okay, so consider these two. Okay, so you can replace this R raised to P minus 1 by A raised to P minus 1. So you can write A raised to P minus 1 is congruent to 1 mod P. Okay, because R raised to P minus 1 is congruent to 1 mod P, so you can replace this R raised to P minus 1 with this one. Okay, so A raised to P minus 1 is congruent to 1 mod P. This is true for any integer, not only the element in between 0 and P minus 1. So if you choose any element Z, A belongs to Z, if that A does not P does not divide A, then you have R raised to P minus 1. This R is a reminder. R raised to P minus 1 is congruent to 1 mod P. As a consequence, we also know that A raised to P minus 1 is congruent to R raised to P minus 1. Then we can easily say that this is multiple of P as well. Okay, that is because what is the meaning of this A raised to P minus 1 minus R raised to P minus 1 is a multiple of P. That is the meaning of this statement. Okay, so if you subtract minus 1, you will get, this implies A raised to P minus 1 minus 1 minus of R raised to P minus 1 minus 1 is multiple of P, because you can cancel this minus 1 and this plus 1, then you will get the same thing. So we already shown that if R is a element in between 0 and P minus 1, then this is a multiple of P as well. Therefore, A raised to P minus 1 minus 1, okay, is also a multiple of P, because this is a multiple of P and this is a multiple of P, then you can get A raised to P minus 1 minus 1 is also a multiple of P. So this proves Fermat's little Fermat's theorem. And as a corollary, you can easily get, if you assume that A is congruent to, if A is any element of Z, then we know that if P does not divide A, then you have A raised to P minus 1 congruent to 1 mod P. Okay, you multiply A both sides, you will get A raised to P is congruent to A mod P. Okay, so if this happens, you can easily get A raised to P is congruent to A mod P. If P divides A, what is the meaning of this? A is a multiple of P. Okay, obviously A square, A cube, any power of A is a multiple of P. So in particular, A raised to P is a multiple of P. Then the difference, A raised to P minus A, is also a multiple of P. Consequently, you can get A raised to P is congruent to A mod P. So in any case, if P divides A or P does not divide A, you will get A raised to P is congruent to A mod P. So A is not a multiple of P, then you can get this result. Okay, this is what we call little theorem of Fermat. Okay, as a consequence of or application of this theorem, there are a couple of examples are discussed in the textbook. The first one is example 20.3. So what is the application? How will you find 8 raised to 103? What is the remainder of this when it is divided by 1, 3? Okay, so we need to observe what is the remainder, what is the value of this place which satisfies this condition. What is the meaning of this? When you multiply, when you divide 8 raised to 103 by 13, then there should exist a remainder. That means if you write 8 raised to 103 is equal to some 13 times q plus r, then how will you find r? So r will satisfy this equation. Okay, so how will you find r? This is the first question. So this is easy to evaluate, because 8 raised to 103 can be written as 8 raised to 12 whole raised to 8 into 8 raised to 7. Okay, so this can be written as 8 raised to 12 is congruent to 1 mod. Okay, so this is 1 into 8 raised to 7 congruent to this is congruent to 1 mod 13, because by Fermat's theorem, by taking a is equal to 8 and p is equal to 13, then 8 to the power p minus 1 congruent to 1 mod p, that means 8 raised to 13 minus 1, that is 12, is congruent to 1 mod p. Then by taking power 8th power, you will get 1 raised to 8. So this quantity 8 raised to 12 whole raised to 8 is congruent to 1 into this is 8 raised to mod 13. Okay, so we know that actually 8 is we know that 13 is a multiple of 13. So 13 is congruent to 0 mod 13. When you multiply, when you divide 13 by 13, then remainder is 0. And you can write 8 plus 5 is congruent to 0 mod 13. From this you can write 8 is congruent to minus 5 mod 13. Okay, so you can replace this 8 by minus 5. So minus 5 raised to 7 mod 13. Okay, so this is the remainder. Okay, the remainder of 8 raised to 103 and remainder of minus 5 raised to 7, both are same. Okay, so next we need to show that this is congruent to how will you write minus 5 raised to 7, that is minus 5 square whole raised to 2, this is minus 5 raised to 4, then minus 5 raised to 3, this is minus 5 raised to 6 into minus 7 mod 13. What is the justification of this? You write minus 5 into minus 5 into minus 5 into 6 times first, then 1 time. Okay, this is minus 5 raised to 6 and this is minus 5 raised to 1. Obviously, what is the value of this? This is 25 raised to 3 and minus 5 mod 13. What is 25? We know that 25 minus 1 is a multiple of 25 plus 1 is a multiple of 16, right? Multiple of 13. Okay, this is 26, then 26 is a multiple of 13, then 25 is congruent to minus 1 mod 13. So you can replace this 25 by minus 1. Minus 1 raised to, this is congruent to, these are all congruent to minus 1 to the power 3 into minus 5 mod 13. Okay, consequently you can write this is minus 1, then minus 1 into minus 5 is 5 mod 13. So you can say that when you divide 8 raised to 103 by 13, then remainder will be 5. So this is one of the examples given in the textbook, so please go through it and also write the other examples as well. A couple of examples are discussed in the textbook as well. Okay, now we move on to the generalization of this theorem. That is what we call Euler's generalization, that is theorem 20.6. This is again a theorem. This is to we use this theorem 20.6 to generalize the previous result. So this theorem says that the set Gn, what is Gn? This is set of all non-zero elements of Zn that are not zero devices, form a group under multiplication moduli. I'll write it as multiplication moduli. Okay, so if you consider Zn, for example, for instance you take Z6. Okay, so what are the non-zero elements of Z6 which are not zero devices? One thing is 0, then what are the zero devices? 2, 3 are zero devices. So the only 2, 3, 4 are zero devices, because 4 into 3 is 12, 12 is a multiple of 6, then that is 0. 2 into 3 is 6, 6 is also a multiple of 6, then that is 0. So these are the only non-zero elements which are not zero devices. So if you consider G6 as 1, 5, so G6 consists of set of all non-zero elements of Zn which are not zero divisors. So G6 is meant by this 1 5. And what is G4? G4 is non-zero elements of Z4 which are not zero divisors. So this is that set. Okay. Similarly, you can actually G4 consists of the relatively prime elements with this 4 or this n. Okay. So we show that this Gn is a group under multiplication modulo n. So how do you prove Gn is a group? We start with a closure property. If you choose any a comma b belongs to Gn, okay, then we will show that AB is also an element of Gn. Okay, so we need to show that AB is not a zero divisor. Okay, it's not a zero divisor, and A and B are obviously and B are non-zero elements. Then AB is we show that AB is non-zero element, and that is not a zero divisor. For that, suppose that AB is not an element of G. What happens? We will arrive at a contradiction if you assume this. Okay, if possible, assume this AB not belongs to Gn. So AB is not an element of Gn means there exists a C such that AB into C, okay, equal to 0, because AB does not belong to Gn means AB is a non-zero quantity. It is not a zero. It is a zero divisor. It is a zero divisor means there exists C such that AB C equal to 0. Now this implies that AB equal to 0 implies that A into BC equal to 0. Okay. So since this B is an element of Gn, and obviously this B is a non-zero quantity, and C is a non-zero quantity, we started with the C. That means if AB is not a member of Gn, then there exists C not equal to 0 such that product is 0, because this AB is a zero divisor. Then A into BC, B and C are non-zero elements. B is non-zero and C is also non-zero elements of non-zero element of that Gn. Then we have BC not equal to 0. This implies BC not equal to 0. Okay. So by definition of this Gn, because Gn consists of set of all non-zero elements of Gn which are not zero divisors. So since B is a member of Gn and C not equal to 0, then we can get if you multiply two non-zero elements, then B is not a zero divisor because B comes from this. So this shows that BC not equal to 0 by definition. Okay. Then this implies BC not equal to 0 implies A not equal to 0. Okay. Oh, sorry, A not an element of Gn. A not an element of Gn, because BC is a non-zero quantity, but if you multiply it with A, then you will get A into BC equal to 0. So A and B are non-zero, A is non-zero, BC is non-zero, product is 0, which shows that A is not a zero divisor. So A will not be a member of A is a zero divisor. Actually A is a zero divisor, because if you multiply A with a non-zero quantity, you will get 0. So this A is a zero divisor. A is a zero divisor means A will not be a member of Gn, which is a contradiction. Okay. Now you can say that AB belongs to, which is a contradiction. A contradiction. Then AB is a member of Gn. Okay, so if you assume AB is not a member of Gn, then there exists a C not equal, a non-zero element C along with the associative property. You can easily prove that A is a zero divisor. So A will not be a member of Gn. So that will be a contradiction. Then AB belongs to N. Okay, so we then we proved that this a Gn has closure property under multiplication modulo N. Okay. Next, obviously we need to prove that the associativity, but we are dealing with the elements of the ring. Then in a ring, the element satisfies the associative property of multiplication. So we need not worry about the associative property of the multiplication of the elements of Gn, because Gn is a subset of the ring Zn. Okay, so it's a multiplication modulo N is always a associative property. So we need not worry about that one. Okay. Now we can easily show that 1 belongs to Gn, because 1 is a non-zero quantity, 1 is not a zero divisor. So obviously 1 is an element of Gn. So this shows that the existence of identity. Now we need to show that this has multiplicative inverse. Every element of Gn has multiplicative inverse. So we write elements of Gn. As this Gn is finite, we write A1, A1, A2, etc. AR. Suppose these are the elements of Gn, and if you pick any element belongs to Gn, we need to show that A has multiplicative inverse. That means if you consider A belongs to Gn, you write or multiply every element of this set with A. So A1, A2, etc. AR. Okay. So this is also Gn because it contains exactly R plus 1 elements. 1, 2, 3, etc. R, and along with one A we have R plus 1 elements. And this is always a subset of Gn containing n R plus 1 elements. Consequently, this set A1, etc. AR is equal to Gn as well, because this is a subset of Gn containing the same number of elements. So we know that Gn contains 1, so obviously this 1 is a member of this. So 1 is either equal to A, or the other way 1 is equal to some AI for some I. So if A equal to 1, then A has multiplicative inverse 1 itself. Otherwise there is another element AI such that A into AI equal to 1, then A has multiplicative inverse. So for every A belongs to Gn, that A has multiplicative inverse. Therefore Gn is every element of Gn has multiplicative inverse. So this shows that the existence of inverse. Therefore Gn form a group. Okay, a group obviously is an abelian group, because Zn is abelian, then A multiplication modulo n B is same as B multiplication modulo n A. Okay, so this is an abelian group. So which proves theorem 20.6. So if we prove this theorem, then we can easily prove Euler's theorem, that is the generalization of Fermat theorem. That is, this is theorem 20.8, Euler theorem. Euler's theorem. This theorem states that if A is an integer, relatively prime to n, then A to the power phi of n minus 1 is divisible by n. That is, A raised to phi of n is congruent to 1 mod n. Okay. How will you prove this? We know that if you choose any A belongs to Z, okay, the only thing is GCD of A comma n is equal to 1. Okay, so if you choose such an element A belongs to Z corresponding to this n, then you can say that A belongs to if this GCD of n is equal to 1, then corresponding to this A, you can get NR such that 1 less than or equal to R less than or equal to n minus 1. If you choose any n satisfying this, then A is, or you can think of this R as B. Okay, I will put it as some B. Then for any, then that B is a member of this inequality, or is an element in between 1 and n minus 1. Obviously, for corresponding to every A satisfying this, then there exists a B. B satisfies this condition, and we know that this A and B, we can say that A is congruent to B mod n. Okay. Obviously, A raised to any k is congruent to B raised to k mod n. That is, A raised to phi of n, any number that is congruent to B raised to phi of n mod n. So it is enough to prove that B raised to phi of n is congruent to 1 mod. Okay, but we already proved that as this B is a member of Zn, because B is in between 1 and n minus 1. So B is a and GCD of we know that a comma n is 1, GCD a comma n is equal to 1 means GCD of B comma n is also 1. Clear? Because of this quantity, we know that the common divisor of a and n is always 1. Then we can say that b and n is also 1. If this n and b has common element d, then that is also a common element of a as well. So we know that the highest common divisor of a and n is 1. Then the highest divisor of n and b will be 1 as well. Otherwise, that there will be a contradiction for this statement. So we have b comma n is equal to 1. Then we can say that b is a non-zero element and b is a is not a zero divisor as well. Not a zero divisor. We know that only the zero divisors are the elements which are not related to prime to n. So since this b is related to prime to n, then this is not a zero divisor. So this implies that b belongs to that Gn. We already proved that what is the cardinality of Gn? Cardinality of Gn is phi of n. Okay? Because Gn contains the elements which are relatively prime to n. Okay, all other elements are zero divisors or 0. So the cardinality of Gn is phi of n. We know that if we multiply b or operating b n times, okay, or phi of n times, not n times, phi of n times, we will get 1. Because b is a member of a group Gn which has the cardinality phi of n. So if you operate any element with the cardinality of Gn times or cardinality of the group times, we will get identity. Okay, here identity is 1. So b raised to, this is phi of n times. This is the order of the group. So b raised to phi of n is congruent to 1 mod n. Okay. So if we substitute this equation in this one, we will get, since b raised to phi of n is 1 mod n, then we can say that a raised to phi of n is congruent to 1 mod n as well. Okay, which shows that a is congruent to phi of n mod, a raised to phi of n congruent to 1 mod n. So this proves Euler's theorems as well. Okay, again a couple of examples are discussed after this theorem. Then you please go through it, and there are some interesting theorems can be proved as a consequence of this. Then that will be proved in the next class.